video for you guys before I leave. Also, a comment for one of the guys who wrote me do the math. Yeah, I saw your comments, and he did correct me. It was 8,500 on the concrete. So yeah, guys, please don't be afraid to correct me if you when I say something here and I get it wrong. Wrong. It's clearly wrong. It was 8,500. I mentioned that in a long time video too. That they pre-stress at 6,000 or something like that, and then the concrete's got to reach 8,500. But yeah, thanks, do the math for that. As far as the rest of your comments go, you're still stuck on 11 and 12 being the issue, as shearing. So yeah, I'll just respect your comments with that. I won't let myself get out of control and tell you that you're so far off base. But I will do this. We'll look at the core samples. I'll do this for some more data. And guys, please, again, if you see me get something wrong, I do this stuff live and real fast, and I can clearly get things wrong. So we don't see any voids in here, pockets inside this sample they have up here, honeycombs, things like that would cause the concrete to fail over right about here as we look at this deck. Here's number 11. So we don't see this core came from somewhere out of these holes, right? That's what we're assuming. And we don't see these honeycombs, things like that, density. Coming over to this now. And maybe you guys are still 11 and 12. Maybe this guy, do the math guy. Let's talk about this being in compression now. So let me play devil's advocate. Okay, this is in compression. And magically, this column, this diagonal in compression resolves itself in the middle here with cracking. Okay, so I'm trying to sell myself that it's under compression. Well, the cracking came because the rebar was too tight, and it buckled, and the rebar buckled and caused this crack. Okay, so I'm still trying to sell myself compression, and it's not failed because on the compression, this right here is a change of direction, right? Wouldn't you see a crack off of here if this was correction? If this was under compression, because now we're only down to what, 4 inch? Well, let's see. Let's do this and try to rotate it. He's right about, well, let's call it, if we look at this plane right here, it's right about 8 inches, and we'll use the top of that. He's right about 12 if we turn this. So 8 to 12, if you turn this, scale this and turn it, this is about 8 to 12. Call it 8 to 13 inches. So if you want an extra 5 inches, I want to say 5. So 4 to 5 inches is what we're looking at from here to here. Do I discount this crack? Well, let's discount an inch. Now we're down to 4 inches. Or you guys can take back your inch. I'm okay with it either way. Now we're saying that the entire bridge structure can hold the load down number 11. It's under compression, and it's only 4 inches of column. So that would discount this guy's comments over here. This guy who, and so I'm critiquing, that's how I'm able to look at this. This guy, Peter Dow, who did an awesome graph here and all that. This presentation like this will sell people on your beliefs. And this is where things can go south. He has down here that this is a zero force member, apparently. This top between number 10, 11 connection and number 12, zero force member. Denny Pate's presentation shows that clearly as a non-zero force member, as a force member. It's got post tensioning in it. It's not. It's got forces going down it. All right, and the canopy gets tied over, as we know. So now down number 11, he has 304 kips. Let's just not hate on him too much. He's got these two apparently under compression. This one's under tension, or is just a failed move. While supporting by the transport, a cantilever end, right? So it goes that direction. No. So this still has, if you pull the compression on this, the tension on it, yeah, this would take the load off of here. I did a video on that, so yeah, I'm game with that. You see, PT bars and members will not be grouted. He's followed what I said on that until they've been removed. All right, let's move on away from that guy. I'm going to delete that page. we have Denny Pate's presentation, and I think in my presentation I was like, I thought they had shims down there too. There are the shims. 1 and 2 shims will take that. And let's go here over. And for clarity, it looks like there is no nylon bushing here. So nylon, 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 the pads. And now we jump over to my man. He's in England, I think. I think it's Mark. Is this Mark or is it, gosh, is Mark or somebody else over there? We were talking about zone of influence, etc., and the comments. So let's look at the decks tensioning. And D1, D2, D3, D4, D5, D6, right? So, and they're symmetrical, and then it goes the other side. So I need to get this up for you. Not that one. Bear with it. I have to look at each screen. All right, so this is interesting. This is, well, wait a minute. So D1, D2, D3, D4, D5, D6. See it? The nephew, the cousin. Right? Set off of that is one from the drain, 1 foot 10 inch on the center line of that duct, and then the 1 foot 4, and I guess 1 4 1 4 1 4. But the center line of that is 1 4, and your cover is about 8 1/8 of an inch right here, and that would be center line of this or the top of it. Invert, not the invert, the bottom. But let's go back to here now. So D1, it's D1 is 12 times 0.06. These are the tendon sizes. It's 173 feet, so you know we're talking about the span that failed. The stressing force, 527 kips. Live end force after anchor set. So it's going to be 471 kips. Look at D2, D3, D4, D5, and D6. 745, 745, 745. There's your symmetry, your equilibrium I like to see. D1 was decided that the closest one to the center of the structure is decided that it would be near half that. Very, very interesting, right? I look at the symmetry of all the others again. D6, 775, 1, 2, 3, 4, 5, and there's this one again. So you see the symmetry is off on that, and they're that zone of, that's a weird thing, isn't it? Remember I talked about nuts and bolts, how which one's going to be doing the work, the one with the most clamping force. Well, the clamping force is clearly hugely different here. So what is the intent, or what is it disclosing about the engineers, what they see, what the designer saw to be an issue, meaning that you must keep it down right there for some reason. I just want to bring that to your attention. I think I brought this to attention in another video, but we're up to probably 100 videos on this topic with me. So again, please comment, correct me if you see me bouncing off the wall there wrong. This is the guy's comments. There are a lot, and I think him and I went down this path before, and I don't like diverting from the agenda, the topic, if you will. If you believe number 11, I just considered number 11 again. Let's put it under compression. Let's say it's going over there, but you can't get shear at it. You cannot get shear. Okay, sorry. You can't get shear from here. We're only down to 4 inches. And yet it's under compression, holding all the way to the structure, as everyone claims, that this is how it comes off from compression on this bridge. And they're now, and he was upset with me agreeing with Denny Pate. That triggered him. It's okay to be triggered, right? Denny Pate says 10 and 11, 10 and 9, that we need to resolve those forces out there. Here's the shim. So clearly this shim, this part right here, they're talking about shimming, would be under D1. That's 1 foot 1 inch over, and it would be under D1, the tendon of D1. Again, let's look at this. If you're claiming that it's shearing off, okay, I don't need that. If you're claiming, let me get rid of that. and get rid of that. If you're claiming that it's shearing off, let's get the photograph here, that this is pushing down, creating these cracks. Why don't I see it reflecting here or here? How come it's not reflecting? How come it's not identifying itself? Let's play devil's advocate. It identifies itself at the bottom under that half-inch gap, cracks, or whatever they show about NTSB. I don't see that. All right, so you guys know where I stand. That it's tendons are failing here. Not just this little. This is not the load transferring, going downwards. This is a tendon failure breaking in the deck. Because he's saying shimming. Nowhere in this meeting did they say we need to put this back in plane. It just says shim it. It doesn't say anything about, and there's photographs of it. This might be of the meeting, the day of the meeting, which shows it clearly in plane. It doesn't show this broken through. Maybe they'll turn up. I think I said that in a previous video also. If they show up, then we know this was just a weird image they put here. And clearly at that point, then the deck is falling down still. But not the truss members. Because we have images of truss members in place during a video. So again, the tendon is center line of this pipe, and we don't see cracks down here. This pipe, you still have some distance to go. This is the drain pipe, but there's no crack identified right here. There's no crack talked about here. There's no crack talked about inside this whole diaphragm underside of deck at all. I just see the failure up top. They should have talked about a lot more. And now, again, the agenda of FDOT putting these papers out, we have to realize we're not getting true data here. We're getting data, but it's not true data. Remember, Denny Pate did not say what they reworded him to say. He said it would give a false sense of security, as reported by in the first report by the OSHA report. So OSHA, it clearly has that marked that way. Why are they soft step it? All right, steel channels to 10 and 9 nodes. 10 and 9. 10 and 9 is the base. It's not the top. 10 and 9 nodes, and post tension bars to capture some of that force that is better than vertical support, which is better than vertical support. Again, they're trying to transfer the loads from 10 to 9 back over to the diaphragm. Of course, not immediately they want, number 11, they want to get that shimmed up under there. My guess is to stop the deflection if it kept going down, to grout it immediately, to stop it, to confine the member literally so it can't break at that point. So again, we're looking at 9 and 10 and number one, deck D1 and D1 over here. So it appears that with that lower post-tensioning numbers that made it a weaker area. And let's go to this. And remember the profile of the canopy. Guys, I swear this is not. I don't swear really. That in the images, that this profile looks like it's inside the node, inside the blister bar. So I have an issue with the locationing of that, but maybe it was changed again. That's a big issue for me. I talked about that. As you post-tensioning, you put stress on that cable, and in that case it's a tube because it's not filled. The fills are out here, and you got issues. Let me go to 167 feet plus 4 feet is what? 171 feet. Go back one. Here's 175 feet from end to end. I think I talked about this before. What's going on here? Your footage is clearly at the end of the outside of the post-tensioning, and you're calling out 171. So that's a kind of a weird thing I have issue with also. Here it is again for more clarity. This is 11 and 12. And let's go down the line again of that. I'm going to work on the assumption that it's under compression now. So it's under compression and pushing off. Well, there's a little bit of concrete right here that should have been busted out. Nobody spoke of that. Nobody's seen it. Nobody knows anything of it. Again, I did this video before. This is on the compression. Right here, we'd have a blowout here too. This is only 2 inches of cover or something like that. All right, with this thing moving down. We don't have it. Here appears to be, I don't know, the number 7 rebar that I keep asking about. It's magically can't be tested. Now, it's just magically can't be tested. I don't get that. All that reinforcement can't be tested. Okay, now right here is where you would see a crack. We don't see it, but you know, when you get invested in this stuff like they do, I'm willing to change still. Here's 9 and 10, incidentally, right next to each other. How beautiful is that? This is where I think the forces, as even Denny Page says, they moved over. We don't see a crack. We see the crack approximately right here within this first zone of influence of the post-tension D1s. Here's D1, and this is D1. So this is with the lower numbers. I'm going to terminate this video, and we're just going to hit this quite a few more times. Again, please tell me if you see that I commented anything wrong, and correct it in the notes, and I'll in the comments, and I'll say thank you, and we'll move on. People will hopefully read the notes and understand it. This is fluid. We won't hate each other for correcting each other. And thank you.